Linear regression. What is linear regression? Well, linear regression is a linear approach to modeling the relationship between a scalar response, or dependent variable, and one or more explanatory variables, or independent variables. Always remember that x, those independent variables, is trying to predict y, the dependent variable. So a simple linear regression depicts the relationship between one dependent and two or more independent variables. So let's consider this following graph with the equation of the line as shown. We have y equals b sub 0 plus b sub 1x plus e. Well, b sub 0 is the y-intercept. So if x were equal to 0, what is the basis for where y starts on that line? It represents the estimated average value of y when the value of x is 0. B sub 1 represents the slope. It also represents the estimated change in the average value of y as a result of 1 unit change in x. In a lot of data science and machine learning terms, you'll hear this as the coefficient or the weight. And then that e is going to be noted as the error term, which is unexplained variance in the model. So the values here, you can see that intercept equals b sub 0 is where y starts when x is equal to 0. Now here we have 6 dots. So this is essentially a scatter plot matrix with 6 data points of x on y. So those are the actual values, and what we did here is we fit a line to best approximate the data. So if we added or had a new variable in the model, a new x, we would have a pretty good idea of where it would fall. It should technically fall on the line, but there's that random error which denotes that it may have some sort of variance instead of falling directly on the line. Now, the method of least squares identifies the line with the lowest total sum of squared prediction errors, the sum of squared errors, or SSE. Now, what we're trying to do is minimize the sum of squared errors. And the reason we're doing this is because we want to have the best approximation of those data points to the line. So we have the sum of squared residuals, which is y minus y, the mean of y squared, is that measure of unexplained variation. Now when we look at the sum of squared errors, we have that sum of y minus y, which is that measure of unexplained variation. And so that's what we're trying to minimize. And then lastly, we have the sum of squares, which is the sum of squared residuals plus the sum of squared error. So let's look at an example of linear regression. We have the independent variable on the x-axis, x, and the dependent variable on the y-axis, y. So here, we have actual observations denoted as these black marks. And then we have random deviations. So we fit a line to best indicate the relationship between x and y. And those random deviation is that error term from the actual versus expected values. Now, when we're looking at the coefficient of multiple determination, what we often use in statistics is r squared. And r squared is a goodness of fit measure on a regression model. It's used to determine the total variance with the help of the independent variables. So how well does a single independent or multiple independent variables predict y? If r squared was equal to 1, then it fits perfectly. It means that our predictors perfectly explain everything in the model, and there is no error. You could think of it in accordance to accuracy of the model. So here we have the types of linear regression, another example. Again, we have a scatter plot matrix, and we're looking at predicting experience on salary. Now these are the residuals. So when you graph in R, the residuals, it will always be a flat line. And then how far on the negative or positive side are those residuals, which is essentially that unexplained variance, that remainder, compared to the actual. So the residuals would be equal to 0 if there was no unexplained variance, if there was no error. But because that's not the case, we get residuals. So SSR, sum of squared residuals, is the sum of y minus y hat squared. And then we have SST, the sum of squares total, which is the sum of all data points y minus the average of all y's squared. Now the reason we have to square these terms is if we just had y minus y, the end result would be equal to 0. So what the squared terms does is it penalizes distances further from the line. And r squared is computed as 1 minus the sum of squared residuals divided by the sum of squared of the total. R squared of a model increase with an increase in the number of independent variables. It's completely contingent on if there's a relationship and orthogonality or independence of those variables. Now, adjusted R squared looks at penalizing a model with too many variables, and so what it does is it readjusts the accuracy of the overall model. Now, R squared can generally increase with an increase in the number of independent variables, but that's completely contingent on if those independent variables are orthogonal or independent from one another, if the predictors are not correlated themselves, and if those predictors have a relationship with y. Because if x has no relationship at all with y, then it won't increase the accuracy of a model. Now the way of computing this, r squared, as we just stated, is 1 minus the sum of squared residuals versus sum of squared total. What adjusted r squared does is it factors in the number of variables as well as the sample size to penalize that model. So we use the r squared calculation to calculate adjusted r squared. We use 1 minus this additional model, 1 minus r squared times n minus 1, which is the sample size minus 1. With samples, we always subtract 1 as an greater estimator of the population, and then divide all that, the number of sample size, with the number of variables in the model minus 1. Standard error of a regression is the measure of variability around the line of regression and can be used the same way as the standard deviation. So standard deviation is for the population. Standard error is for the sample. So you say standard error is computed as the square root of the sum of squared error divided by the number of observations in that sample and the total number of variables in the model. And now it's important to note that we want to have confidence in regards to our models and their accuracy. So when you think of the standard bell curve, one standard deviation away from the mean will represent 68% of the population. So 68% of the population will fall within one standard deviation from the mean. Within two standard deviations, plus or minus, any samples will fall within a 95% accuracy of the population. And then 3 standard deviations away would give us about a 99.7 confidence interval. Now, dummy variables are one way of many ways to encode data. So each in a dummy variable would be coded as 0 or 1. What dummy variables do, they assume the intercept is different, that the slopes are constant across categories, and it allows us to work with qualitative data, like nominal or ordinal or factors. And it incorporates large residuals and influence as measures. So what's an example of a dummy variable? Well, males and females. And so you see, the slopes of these lines are the exact same, but the y-intercept of where these start show that females start higher than males on this scale. So when we encode this data, and we could encode males as 0 and females as 1, or females as 0 and males as 1, once we do that, now we can use that data to compare these different groups, females and males. An interaction effect assumes the interaction between pairs of x variables. It includes a two-way cross-product term and can be combined with other models such as dummy variables in a regression model. So, what's an example of an interaction effect? Well, let's say we're trying to predict cancer, and I'm a health researcher, and so from all of the research, I've known that smoking predicts lung cancer. I also know that excessive drinking predicts lung cancer. But what if I'm interested to see if people who smoke and excessively drink are more likely to get lung cancer than people who only smoke or only drink? Well, an interaction term would allow me to essentially multiply the amount that someone smokes and the amount that someone drinks and create a new variable in that model to see if there is an interaction effect between those two predictor variables on the outcome variable y. So you see in the example here, y equals 1 plus 2x1 plus 3x2. x1 and x2 are independent variables, plus 4x1, x2, and that's the interaction term. Let's say we're building the model to where x2 is set as equal to 1. So we have y equals 1 plus 2x1 plus 3 times 1 plus 4x1 times 1. And so when x2 is equal to 1, the slope of that model is 4 plus 6x1. When we have it where x is equal to 0, we see it's 1 plus 2x1. So the slope is minimized. So the effects of x1 on y is measured by 1 and the weight of b1 plus b3x2, respectively, in this lower model.